Hello, everybody, all of you people of the class. Yeah, welcome to this installment or this knowledge nugget. It's my new favorite term, by the way, knowledge nugget, which is what I provide for you with every video. It's kind of like a little contained capsule of knowledge or knowledge nugget. Okay, so we want to continue today with talking about acid-base chemistry. And where we left off last time is we got through talking about the pH scale, we talked about the pOH scale, we talked about pKa, and from those three things, we can begin to start to define exactly how to quantify a specific constant or a specific solution of acid. Okay, so if we have, for example, if we have a weak acid and a strong acid, we're going to treat these systems in kind of different ways. Oops. Let me turn that down. Okay, so we have we want to be able to quantify the H3O plus and the pH. Oops, let me write that a little better. pH of strong and weak acid solutions. Okay. We have two sources of H plus, two possible sources of H plus. When we are considering the total concentration of H+. Okay, we have the acid dissociation, which is just with our generic acid, we have HA, aqueous plus water, liquid goes to H3O plus, aqueous plus A minus aqueous. Okay, so we get a source of H3O plus in from this reaction, but at the same time, since this is still a reaction that's happening within water, we're assuming this is all aqueous, by the way. We also have the autoionization of water. Okay, so in this case we have H2O reacting with H2O. Probably the weirdest chemical reaction you will ever encounter, water reacting with water, to form H3O plus aqueous and OH minus aqueous. Okay, so we have two sources of H3O plus, and we need to determine the total concentration of H3O plus based on these two sources. So it turns out that except for extreme dilution or extremely diluted acid solutions, autoionization contributes a negligible quantity of H3O plus. Okay, so even though it's a source of H2O plus, we can actually pretty much always ignore it. Okay, and what do I mean by extremely dilute? So if you get to the level of 1.0, oops, let's change this to the concentration of the acid, approximately 1.0 times 10 to the minus 5 and less, you have to consider autoionization. But anything greater than that, so if you have an acid concentration greater than 1.0 times 10 to the minus 5, you can basically completely ignore the autoionization. Okay, and that's because the concentration of H3O plus for the autoionization of water is approximately 1.0 times 10 to the minus 7. Okay, so that's how much you're going to get from autoionization at 25 degrees C. And and you can see that if you have a number that's greater than 1.0 times 10 to the minus 5, that means that it's going to be more than 100 times that which you're going to get from autoionization, in which case you can completely ignore autoionization. Okay, let's talk about strong acids first. How do we quantify the H3O plus concentration? And then we'll come back to weak acids in just a second, okay? So strong acids. Now remember, a strong acid is an acid that completely disassociates in solution. Okay, so we have complete ionization. And that means that if we have some solution, a certain concentration of a strong acid, that means that this is exactly going to equal the concentration of H3O plus that we make in solution, because we have HA reacting with H2O to form H3O plus and A minus. Okay, this is a one-way reaction. We basically are taking all of the acid and we're transforming it into H3O plus. Okay, so for example, if we have a 0.10 molar HCl solution, that means that we have an H3O plus concentration of 0.10 molar. Okay, and since we have the H3O plus concentration, we can calculate the pH rather easily, which is just negative log of 0.10, which is equal to 1.00. Okay, so we have the pH of this solution, and it's based entirely on the concentration of the initial acid for a strong acid. Okay, strong acids are pretty easy. Weak acids are a bit more complicated. So, do you guys remember the equilibria stuff we did in the last chapter? Well, this is where it comes in really handy. Okay, so if we have for a weak acid, it turns out that since we don't have complete dissociation, the H3O plus concentration does not equal the concentration of the initial acid. Okay, so we cannot make that assumption. As a matter of fact, the H3O plus concentration is always less than the initial acid concentration. Okay, and that means that we have an equilibrium. So we have HA reacting with water to form H3O plus and A minus. Okay, so we have all of these things in solution. We have some equilibrium constant, which for an acid, remember, we call the acid dissociation constant, or the acid ionization constant is another word for it. So using this, we can actually set up an ice table, and we can use ice tables to determine the equilibrium concentration of H3O plus. So on this side of the equation, we have HA. Remember, we don't include liquid water. Okay, so that's the reactants. And the product side, we have H3O plus and A minus. Okay. Now, initially, say we initially have some 0.10 molar weak acid. And we want to know what the H3O plus concentration is. Okay. So that means that for our initial concentration of HA, we have 0.10 molar. For H3O plus, we have 0, and for the A minus, we have 0. And then we allow the reaction to take place. Okay, so this is represented as the change. And with this, we have negative X, right? We're going to take away a certain amount of the initial undissociated acid, and we're going to create the exact same amount of H3O plus and of A minus, because it's a one-to-one stoichiometric relationship. At equilibrium, we just add these together, just like we did before, and we have 0.10 minus X and X and X. Now, do you remember what we do from here? We know that Ka is equal to the products, so that would be H3O plus times the reactants divided by the products divided by the reactants, excuse me. So at equilibrium, we can write this as X times X over 0.10 minus X, which is equal to X squared over 0.10 minus X. Okay, so here we want to solve for X. Solve for X using the quadratic formula, okay? Or we can assume that 0.10 is much greater than X, okay, to simplify. So either way, the same stuff you learned from the last chapter. We can apply those same principles here. Let's do an example. So let's say we have a 0.100 molar HCN solution. This is cyanic acid. Okay, 0.100 molar HCN solution. The Ka for HCN, if we look up in table 16 I can't remember the table number. 16.2 maybe table. I can't remember. It's somewhere in your book. There's a table that lists all the Kas of the weak acids, and this one is given as 4.9 times 10 to the minus 10. Okay, so it's quite a weak acid, and we want to know the H3O plus concentration. And we also want to know the pH. Well, to find the pH, we have to know the H3O plus concentration. So let's go through and figure this out. First thing we want to do is set up the reaction equation. So I have HCN reacting with water to form H3O plus and Cn minus. Okay, and of course with the equilibrium expression Ka. Let's set up an ice table. So we have ICE. On this side we have HCN. On the product side we have H3O plus, which is what we're interested in, and we have Cn minus. Initially we have 0.100 molar of HCN, 0 molar of H3O plus, and 0 molar of Cn minus. At the change, we're going to represent the change as negative X. That means that we gain plus X of H3O plus and plus X of Cn minus. Then at equilibrium, we have 0.100 minus X, X, and X. We set this up for Ka. We have 4.9 times 10 to the minus 10 is equal to X squared over 0.100 minus X. Okay, where this top part I've just multiplied these two together to form X squared. Okay. Now, I have such a small Ka value here that this means that my acid is extremely weak, which means that X, or the amount of acid that actually dissociates, will be very, very, very small. So I'm going to go ahead and assume that x is much less than 0.100, and that means that I have 4.9 times 10 to the minus 10 is equal to x squared over 0.100. Solving for x, we have x is equal to the square root of 4.9 times 10 to the minus 10 times 0.100, and this ends up equaling 7.0 times 10 to the minus 6. Okay, so that equals x, and that equals the H3O plus concentration. Okay, now let's check our assumption back up in here. Let's check this assumption. X is 7.0 times 10 to the minus 6. It's very clear that this is less than 5%. I think it's like 0.05-ish percent. 0.07% of that number. Yeah, so we are very good. About 1,000 times less than we need to be. So assumption is good. We can move on with our life. This is the concentration of H3O plus in solution. And now we want to calculate the pH. So the pH is given by the negative log of that concentration, 7.0 times 10 to the minus 6. Oops. Okay, and I don't have this calculated, so I'm going to quickly put this into my calculator. Okay, it turns out that this is 5.15. 5.1, yeah, 1.5. Okay, so that's the pH, and that's the concentration. So we've solved the problem using equilibria. So not so bad, right? We learned how to do all of this before. And it turns out that every time you look at a new weak acid, it always kind of looks the same. Okay, so it actually gets pretty easy to do this over and over. All right, let's do another example. Let's find the pH of 0.100 molar HClO2. Okay, so HClO2, again, write out write out the reaction first. So we have aqueous HClO2 reacting with liquid water to form H3O plus and ClO2 minus. Okay. If we look in table 6.5, okay, so it's 16.5, table 16.5, we find that the Ka for this acid is equal to 0.011. Okay, 0.011. This is quite a bit higher Ka, so I may not be able to assume that that X is less than the initial amount. So let's go through and do the ice and see what happens. So we have ICE HClO2 H3O plus ClO2 minus. Okay, and Ka is equal to 0.011. Okay, initially we have 0.100 moles of HClO2, 0 of H3O plus, and 0 of the associated anion, or the dissociated anion. We're going to represent the amount of change as X, so X gets taken away from here, and X gets added to H3O plus and to ClO2 minus. At equilibrium, we have 0.100 minus X, and we have X and X. I really hope you guys can hear that. That's my youngest daughter. I think she's pretending to be a... oh man, I cannot think of the word. Parrot. I could only think of the word in German. I could... Papagei. I couldn't think of the English word. Anyway, sorry. She's pretending to be a parrot at the moment. Okay, so where are we? Yeah, we have Ka, so 0.011 is equal to the equilibrium of the equilibrium concentrations of the products multiplied together divided by the equilibrium concentrations of the reactant. Now, last time we assumed that this was less than 0.100. Let's do it again and see what happens, okay? So let's assume x is less than 0.100. So we have x is less than 0.100. We have 0.11 is equal to x squared over 0.100. Then we have x is equal to the square root of 0.01011 times 0.100. And x ends up equaling, let's see here, 0.033. Oof. Okay, this is a problem, right? Because if we compare it, 0.033, 0.100, if we look at the percentage of that times 100, we end up with 33%. Yikes, right? That means that we are way above the 5% cutoff threshold. So this is a bad assumption. Okay, it's a bad assumption. That means that we have to use the quadratic formula, right? So use quadratic formula with 0.011 is equal to x squared over 0.100 minus x. We have to get it into quadratic form first. Since we did a bunch of this in the last chapter, I'm going to skip the actual math here, and we end up with x squared plus 0.011x plus, minus 0.0011 is equal to 0. Okay, now we have A, B, and C, and we can plug that into our handy dandy, what is it called? Quadratic formula. Handy dandy quadratic formula. Which you guys should all remember from the beautiful Quadratic Formula song. Sing it with me. You ready? Negative b, plus or minus square root, b squared minus 4ac, b squared minus 4ac over 2a, Woohoo! Actually, you guys... Somebody told me that you guys know different versions of this, and I think we sang different versions in class before the pandemic, but to be honest, time has been passing so weirdly that it's been hard for me to remember exactly what we did or didn't cover in the times before the pandemic, right? It's becoming so much of a blur. It's almost like real life doesn't even exist. Okay, this is the quadratic formula, and all you have to do here, as you recall, is plug in these values above, and you get two answers. You get an x plus and an x minus, depending on whether you use the plus here or the minus. Okay, so we get two answers. X plus is equal to, in this case, 0.028, and x minus is equal to negative 0.039. Of course, we cannot have a negative number here because that means that we would gain mass. We cannot gain mass because that breaks many of the laws of thermodynamics. And because of this, this is unphysical. So the only answer we can possibly use is 0.028. that means that this is our H3O plus concentration. So X is equal to 0.028 is equal to the H3O plus concentration. We have the H3O plus concentration. We want the pH. So now we just plug it into our formula for pH. Negative log of 0.028 is equal to 1.55. Okay? This is our pH for this system. Okay? So you saw a case where this assumption fails. Okay? And you can kind of tell in the beginning that it was going to fail because the Ka was so large. When you have a large Ka, generally speaking, you can't make that assumption simply because it's a fairly strong weak acid. Okay, I'm going to stop there for part 1, and we'll be back for part 2 later on. Go get some snacks, get a good stretch. When you come back, we will continue our discussion. And yeah, hopefully this time, hopefully this time you'll come back, right? See you then.